Somewhere in the deep sky, gravity does something that feels almost like a rule change. Not louder, not meaner, just stricter. Paths that used to include an escape route begin to close, until outward is no longer a future you can choose. A boundary appears in space-time itself, an event horizon. We don't see that boundary directly. We see what it does to the neighborhood around it. Hot gas drawn into a disk, brightening as it spirals inward. Light bent into a ring around a darker center, the shadow carved by extreme curvature. Stars tracing tight, faithful orbits around something compact and unseen. And sometimes, a faint tremor in space-time, a chirp that rises and then settles into a final, fading tone. Evidence arriving in different languages, all saying the same thing. That's the intrigue of black holes. They hide their interiors, but they leave clean, testable signatures outside. They are simple at the center, yet endlessly detailed in the matter and light that gather around them. And the more carefully we measure, the more the mystery becomes a map. Now, gently, we let the universe stay out at a distance for a moment. We turn toward the smaller version of the same idea, here in my office. Because some nights, this room behaves like a kind of metaphor, a place where the light pools in one region and thins at the edges, where stray papers drift inward toward the desk lamp's glow, and the corners fall away into a softer darkness. Not because anything is pulling them with force, but because the way the room is arranged gives everything an easy path toward the center, a quiet geometry, a gentle inward bias. Things aren't quite what they seem when I look around. The rest of the room is dimmer, as if the light can't quite find a clean route back out again. And on the blotter, right at the center of that glow, there is a thick folder waiting to be opened. Its label is plain. Black holes, event horizons, accretion disks, the quiet physics of gravity. Why hello there. For those who don't know, I'm Madeline Rowe, an astrophysicist by training and a private eye by habit. I collect evidence that arrives as light, as timing, as motion, and as tiny distortions in space itself. If these case files help you unwind, you might consider subscribing. It tells the algorithm we should keep the lights low, keep the science precise, and keep the pace gentle. For this case, we won't chase myths. We'll follow the simplest, cleanest facts. A black hole is not a cosmic vacuum cleaner. It doesn't reach out and grab distant things with special suction. From far away, its gravity looks like the gravity of any object with the same mass. The difference is what happens very close in. Close enough, the geometry of space-time tilts in a particular way. Close enough, there is a boundary that acts like a one-way door. That boundary is the event horizon. It is not a wall. It is not a surface you can touch. It is a line in space-time, the edge of the region where getting out is no longer a possible future. From inside, every path you can take points deeper inward, the way every future pointing direction on a map might point south if the coordinate grid has turned. That word, horizon, is fitting. It is like an edge you can approach and cross, but you cannot use it to send a signal back to the place you came from. So we begin with a simple scale, a mass, a radius, and a number that tells us when gravity becomes extreme. For a non-rotating black hole, there is a characteristic radius often called the Schwarzschild radius. It is proportional to the mass. More mass, larger radius. Less mass, smaller radius. It is the distance from the center where the escape speed matches the speed of light in a Newtonian analogy. But the real statement is geometric. At that radius, the event horizon sits in the simplest black hole solution of general relativity. Now here is one of the most calming truths in this subject. The event horizon is not, by itself, a place where the laws of physics explode. In the mathematics, the horizon can look strange in certain coordinate choices, as if time stretches and stalls. But that strange behaviour is often a property of the coordinates, not a physical singularity. A better coordinate map can glide smoothly across the horizon. Let's make that idea practical, using signals instead of metaphors. Imagine you're far away, watching an object fall inward, and it sends a steady series of light pulses back towards you. 1 pulse per second by its own clock. At first, you receive them almost normally, spaced in time the way you expect. But as the object drops deeper into the gravitational field, 2 things begin to happen to those outgoing pulses. They climb out of a deeper gravitational well, so they arrive with less energy, stretched to longer wavelengths. That is gravitational redshift. And the spacing between pulses as you receive them also stretches. Not because the infalling clock feels slow to itself. Locally, it still ticks, calmly, 1 second after another, but the geometry changes what it means for a pulse to escape and reach you. And it changes how successive pulses are separated in the time coordinate you're using far away. So from a distance, the story can look like a slow fading. The object grows dimmer, the pulses grow redder, the intervals grow longer. It's not that the horizon is a physical stall point. It's that the outward communication you rely on becomes increasingly costly in the bookkeeping of signals. And the bookkeeping depends on the coordinates you choose. If you choose coordinates that are well behaved at the horizon, the crossing itself is not a special event in the equations. No infinite alarm bell, no singular spike in local physics. Just a boundary defined globally. What can still send a message outward and what cannot. This is where the case file offers its first gentle paradox. A distant observer watching an object fall inward can describe the fall in a way that seems to slow near the horizon. Light from the falling object becomes more red-shifted, and its ticks appear to stretch out. From far away, the approach can look asymptotic, as if it never quite finishes. But the falling observer's own clock tells a different story. For them, the crossing happens in finite proper time. Their heartbeat does not have to wait for infinity. They cross the horizon without a special local alarm going off, assuming the black hole is large enough that tides at the horizon are small. 2 descriptions. 1 reality, different bookkeeping. It helps to remember that time is not a single universal river here. In relativity, time depends on the path you take through space-time. Proper time is what a clock measures along its own world line. Coordinate time is a label you choose to organize a whole region, like a grid you draw on a map. Some grids are convenient far away, but clumsy at the horizon. Other grids are built to be smooth at the horizon, like coordinates that ride along with infalling light or infalling observers. In the quiet language of geometry, the horizon is a place where the light cones tip. A light cone is a picture of what directions in space-time are possible for signals that travel at or below the speed of light. Far from the black hole, the cone points mostly forward in time, and you can choose to move inward or outward in space. Closer in, the cone leans. At the horizon, every future direction points inward because the outward direction has become space-like in a way that cannot carry causal influence outward. And inside, inward is no longer just a direction in space. It becomes as unavoidable as tomorrow in the classical picture. That word, unavoidable, can sound dramatic. So let's soften it with a clear limitation. Everything we say about the deep interior rests on extending classical general relativity all the way down. We expect that at some extreme scale, quantum gravity matters and the classical description is incomplete. But the horizon, the accretion disk, the jets, the waves we detect, and the images we reconstruct are all about the region outside, or just near, the horizon. That region is where hard science does its calm work. Before we move outward to the glowing disk, we should pause on a detail that often surprises people. Tidal forces at the horizon depend strongly on the mass of the black hole. A small black hole has a small horizon radius, so the curvature changes rapidly over short distances. That can mean strong tides near the horizon, the classic spaghettification story. A supermassive black hole has a much larger horizon radius. For the same relative position near its horizon, the gradient can be gentler, at least until you travel deeper. So in a counterintuitive way, the largest black holes can be the calmest at the very boundary, in terms of local tidal stress. Now we turn to rotation, because most astrophysical black holes are expected to spin. The rotating solution is called the Kerr black hole. Spin changes the neighbourhood. It introduces frame dragging, where space-time itself is pulled around like a slow whirlpool. If you get close enough, you cannot remain static with respect to the distant stars, because the geometry insists on a bit of co-rotation. Outside the horizon, there is a region called the ergosphere, where that dragging becomes especially important. In the ergosphere, the idea of standing still relative to infinity stops making sense. But even this is not a mystical effect. It is a precise statement about the geometry of a rotating space-time. Spin also changes the location of the innermost stable circular orbit, often shortened to ISCO. The ISCO is the last radius where a particle in a thin disk can orbit stably without plunging inward. For orbits that rotate in the same direction as the black hole's spin, the ISCO can move inward. For counter-rotating orbits, it can move outward. This matters because a thin accretion disk often ends near the ISCO, and what happens at that inner edge shapes the radiation we observe. And that brings us to the warm, luminous part of the case file. Not the black hole itself, but the matter around it. Because astrophysical black holes are most often detected by their surroundings, by a companion star that wobbles, by gas that heats as it spirals inward, by photons that leave fingerprints in spectra, by plasma that organizes into jets, by waves in space-time from mergers. Accretion is the quiet engine behind much of this. Matter falls in, but not straight down, because in the real universe, matter usually has angular momentum. Angular momentum is a kind of rotational budget. To move inward, gas must redistribute that budget, sending some angular momentum outward so some mass can drift inward. That redistribution happens through stresses in the disk, and that word, viscosity, can be misleading if you picture ordinary syrupy friction. In most accretion disks, the microscopic viscosity of the gas is far too small to move angular momentum outward fast enough. If the disk had to rely on simple particle collisions, it would evolve painfully slowly, and many luminous systems would be hard to explain. So astrophysics looks for a different kind of stress, and the leading answer is magnetic. Even a weak magnetic field, threaded through a disk that rotates faster on the inside than on the outside, can become unstable in a productive way. This is the magnetorotational instability, often shortened to MRI. It turns orderly shear into turbulence. It stretches magnetic field lines, tangles them, and creates correlated motions that act like an effective friction, not at the level of single particles, but at the level of the flow. The result is real transport. Angular momentum is pushed outward, mass is allowed to drift inward, and as that drift happens, orbital energy is converted into heat. Because the detailed turbulence is complex, disk theory often summarizes it with a simple parameter. You may hear this called the alpha prescription, where the stress is written as a fraction of the local pressure. It's not a claim that the disk literally has a constant viscosity the way a lab fluid might. It's a practical way of keeping accounts, so the math can connect to observable luminosities and temperatures. So when we say viscosity in this context, we often mean magnetized turbulence that does the same job. It moves angular momentum outward, and it sets the pace at which the disk can feed the center. As the gas spirals inward, gravitational potential energy turns into heat. The disk glows. In the thin disk picture, the disk is geometrically thin and optically thick. Each radius radiates roughly like a blackbody, with a temperature set by the local heating rate. When you add up all the radii, you get a multi-temperature spectrum. For stellar mass black holes, that thermal peak can land in soft X-rays. For supermassive black holes, it can shift down toward optical and ultraviolet bands. This scaling is part of why the same underlying physics produces very different looking sources at different masses. Sometimes the disk is not the whole story. Above the disk, there may be a hot, tenuous region called a corona. The corona can upscatter softer photons to higher energies through inverse Compton scattering. This produces a hard, power law-like component in the X-ray spectrum. That hard radiation then shines back onto the disk, creating a reflection spectrum. In the reflection spectrum, atomic features, especially ion lines, are broadened and skewed by relativistic effects close to the black hole. Those broadened shapes become a tool for studying the strong gravity region, and there is another tool that is even quieter, but remarkably direct. Time delays. If the corona brightens suddenly, like a brief flare, some of those hard X-rays travel straight to us, but some strike the disk first. They reflect, they fluoresce, they are reprocessed into a slightly different spectrum, and because that reflected light takes an extra path, it arrives a little later. That delay is an echo, a reverberation. When you measure the lag between the primary coronal emission and the disk's response, you get a distance in light travel time, not a metaphorical distance, a literal one measured in seconds for stellar mass systems and in longer lags for supermassive systems. In practice, the analysis is careful. You look at different energy bands, you identify where the reflection features contribute most strongly, like the ion line region. You compute cross-correlations or frequency-dependent lags, and you build a model that connects the observed timing behavior to geometry. How high the corona might be above the disk, how far inward the reflecting region extends, and how strongly general relativity is shaping the paths. This is one of the most satisfying things about black hole astrophysics. Even when the black hole itself remains dark, the system around it is chatty in the language of time. A flash, a response, at a measured delay. And from that delay, a map begins to form. So spectra tell us how fast matter is moving and how deep in the gravitational well it shines. And timing tells us how the parts of the system are arranged in space, even when we cannot draw them with a telescope. It's still inference, still modelling, still error bars, but it's inference with a ruler made of light. If you let that idea settle for a moment, it becomes almost meditative. A disk of gas, a hot corona, photons rising, scattering, returning. A conversation between matter and space-time, recorded in the fine shape of a spectrum. There is also a gentle limit built into accretion. If a source radiates too brightly, radiation pressure can push back against infalling gas. In simple spherical symmetry, this balancing point is called the Eddington limit. In real disks, geometry and magnetic structure can complicate the story, and some systems can exceed Eddington for periods under particular conditions. But Eddington remains a useful yardstick, a calm way to compare how intensely different black holes are feeding. And a yardstick is helpful because it doesn't just measure what gets in, it also hints at what gets pushed away. As disks brighten, they can drive winds, not narrow beams like jets, but broader outflows that lift off the disk's surface and carry mass, momentum, and energy back into the surrounding environment. Sometimes these winds are shaped by radiation pressure, sometimes by magnetic forces, often by a mixture that depends on geometry, ionization, and how the inner flow is arranged. This is one reason the Eddington limit is best treated as a scale, not a cliff. The classic derivation assumes spherical symmetry and a simple balance of forces. Real accretion can be anything but spherical. A thick disk can funnel radiation in certain directions, allowing inflow along some paths even while other regions blow material outward. And if photons are trapped and advected inward in a very dense flow, the system's luminosity can behave differently from the simplest picture. Observationally, winds leave signatures, absorption lines, blue shifted features that say, quietly, this gas is moving outward, and they remind us that accretion rate is not always the same as growth rate. Not all the gas that approaches the hole ends up crossing the horizon. Some of it is turned around, redistributed, and returned to the galaxy as feedback, which sets us up for the other kind of outflow, the one that stays narrow and fast. Because sometimes the system doesn't just breathe outward, sometimes it launches a jet. Now we add one more piece to the scene, and it is a striking one. Jets. In some accreting black holes, plasma is launched in narrow beams along the rotation axis. These are relativistic jets, and they can extend far beyond the host galaxy's central region. The leading physical picture ties jets to magnetic fields, threading the inner accretion flow, and to the spin of the black hole, with mechanisms that can extract rotational energy. A rotating black hole, a magnetized plasma, and a structured disk can form a kind of electromagnetic engine. But not every black hole produces an obvious jet. Even our own galactic center black hole, Sagittarius A star, appears relatively quiet compared to the dramatic radio-loud active galaxies. Quiet, still powerful, just fed sparingly most of the time. So how do we know black holes are there at all? We look for what orbits them. We look for what heats around them. We look for what falls toward them and how it shines. One of the earliest and most reliable routes is through binary systems. A normal star and an unseen companion orbit a common center of mass. By measuring the star's motion, its Doppler shifts, and its orbital period, we can infer the minimum mass of the unseen object. If that minimum mass is too large to be a neutron star, we have a strong black hole candidate. In these systems, the accretion disk often announces itself loudly in X-rays. Gas pulled from the companion forms a disk and heats as it spirals inward. The inner regions can reach temperatures that produce X-ray emission. Variability on short timescales can hint at small spatial scales, because light cannot vary faster than it can travel across the region producing it. And that one idea, light travel time, quietly becomes one of our best rulers. Because black holes come with a natural set of scales that all grow in proportion to mass. There's a natural length scale set by gravity and the speed of light, often called the gravitational radius. And there's a natural time scale, the time light takes to cross that region. You don't need to memorize formulas to use the logic. If a black hole is 10 times more massive, its characteristic size is about 10 times larger. and the characteristic times in its immediate neighbourhood, orbital periods near the inner disk, light crossing times, the cadence of many variability features, tend to stretch by about the same factor. This is one reason stellar mass black hole systems can flicker and change state on human-friendly timescales. The inner disk is small, the orbital times are short. So you can watch an accretion flow reorganize itself in minutes, hours, or days. Supermassive black holes live on slower clocks. Their inner regions are larger. Their orbital times near the horizon are longer. So similar physical processes can unfold over days, weeks, or months, depending on the mass and the details of the flow. That scaling is not just a poetic detail, it's a consistency check. If a timing feature appears at a certain frequency in a stellar mass system, and something analogous appears in an active galactic nucleus at a much lower frequency, you can ask whether the ratio matches the ratio of masses, at least roughly. It's one of the quiet ways astrophysics triangulates what kind of engine is present. It also helps us stay grounded when we talk about near-horizon regions. We may not resolve them with a camera in most cases, but time gives us an indirect resolution. If something changes rapidly, it must come from a compact region. If it changes slowly, it may come from a larger region or from a slow process. So the universe gives us two languages for the same neighbourhood. Images, when we're lucky and careful enough to reconstruct them. And timing almost everywhere, because even distant light curves carry the imprint of size and motion. With that in mind, the disk becomes more than a picture. It becomes a clock. And in some cases, quasi-periodic oscillations appear, narrow peaks in a power spectrum that likely reflect characteristic timescales of motion in strong gravity. For supermassive black holes, we have a different kind of evidence, slower and grander. We track stars orbiting the galactic center. We measure their positions year after year, and we map their orbits. From those orbits, we infer a mass of millions of suns packed into a region too small and too dark to be any ordinary cluster of stars. We can also see flares and variability from gas near that central object, a reminder that even a quiet black hole is rarely perfectly still. And sometimes the flare is not just a knot of gas. Sometimes it begins as a whole star. A star passing too close to a black hole feels a difference in gravity across its own diameter. The near side is pulled more strongly than the far side. Those tidal forces can stretch the star, distort it, and, if the encounter is close enough, tear it apart. There is a useful distance scale here. The tidal radius is roughly where the black hole's tidal field overcomes the star's self-gravity. If that tidal radius lies outside the event horizon, the disruption happens in full view of the universe. If it lies inside, the star can disappear with far less electromagnetic drama. So tidal disruption events, often called TDEs, tend to be especially informative for certain black hole masses. They are a kind of natural experiment, controlled not by engineers, but by orbital dynamics. After disruption, the star's debris does not fall in as one piece. It becomes a stream, then a spread of orbits. Some material is unbound and escapes. Some remains bound and returns toward the black hole. As it returns, it can circularize, form a temporary accretion flow, and produce a bright flare across multiple wavelengths. What we observe is not the star itself, but the aftermath written as a light curve, a rise, a peak, a decay, often with spectral features that evolve as the debris changes temperature, ionization, and geometry. TDEs are important for another calm reason. They reveal black holes that are otherwise quiet, black holes that are not currently bright active galactic nuclei. A galaxy can look ordinary for centuries, and then, for a few months or years, a TDE can switch on a luminous signal that says unmistakably there is a massive compact object at the centre. And then there is the evidence that feels almost like a photograph, though it is actually a reconstruction, the Event Horizon Telescope, a planet-sized interferometer, a network of dishes spread across Earth, synchronized, collecting radio waves at millimeter wavelengths. The data are not an image at first. They are measurements of interference patterns, a sampling of spatial frequencies. They must be calibrated, stitched together, and reconstructed using careful algorithms that account for the incomplete coverage. The result is a bright ring with a central dip, consistent with the shadow predicted by general relativity for emission from hot plasma near the horizon. It helps to name what that shadow means. It is not the event horizon itself painted black like ink. It is a gravitationally lensed silhouette, shaped by photon trajectories in the strong gravity region. Some light rays are bent so strongly that they circle, or nearly circle, before escaping. This creates a ring-like bright feature. Other rays fall inward and do not return, creating a darker centre. The size of that shadow depends mostly on the black hole's mass and distance, and only weakly on spin and viewing angle in many models. And once you accept that the shadow has a reliable scale, the next quiet question is shape. Why a ring? And why, so often, a ring that looks brighter on one side? Part of the answer is geometry. Near a black hole, there is a region where light can be bent so strongly that it can loop around before escaping. Some rays skim close, curve partway, and leave. Some circle more than once, briefly trapped in a near orbit before they either fall inward or find a route outward. This piling up of bent paths helps create a bright, narrow feature. The ring is where many photon trajectories concentrate, but the ring's brightness is also a story about motion. The emitting plasma near the hole is not sitting still. It is orbiting fast and in a strong gravitational field. When material moves toward you, its light is boosted. When it moves away, the light is diminished. That is relativistic Doppler beaming layered on top of gravitational redshift. So the side of the flow that is coming toward our line of sight tends to look brighter, and the receding side dimmer. A crescent emerges not because the black hole is off-center, but because the disk's rotation gives one side a natural advantage in the light it sends our way. Then gravity does its final quiet trick. It bends and magnifies the whole scene, so the bright crescent wraps into a ring-like structure around a darker center. And now we can name the two famous cases where this physics meets real data. Sagittarius A star at the center of our galaxy, and the black hole in the galaxy Messier 87, often called M87 star. Two very different masses, two very different distances. And yet, by a coincidence of scaling, the angular sizes of their shadows are comparable when projected on our sky. This is the kind of detail I love as a detective. Not a flourish, a check, a consistency that comes from physics doing the same thing at different scales. Now we add the newest and perhaps most quietly profound kind of evidence. Gravitational waves. When two black holes orbit each other, they radiate energy in ripples of space-time. The orbit shrinks, the frequency rises, the signal sweeps upward in a chirp. Then comes a merger, a brief, violent rearrangement of geometry. And after that, the remnant black hole settles. It rings down like a struck bell, except the ringing is in space-time itself, and the tones are set by mass and spin. Those ring-down tones have a name, quasi-normal modes. In general relativity, a perturbed black hole relaxes to a final equilibrium characterized by only a few parameters. mass, and spin, and in ideal mathematical completeness, charge, though astrophysical black holes are expected to be nearly neutral overall. This is the spirit of the no hair idea. Details of what fell in are washed away, leaving a clean final state. If you let yourself rest with that, it becomes soothing. Complication falls inward. Simplicity remains outside. The universe keeps careful accounts, but it does not keep every receipt. Now, to keep our science grounded, we'll say this carefully. The no hair statement is most exact in the idealized stationary solutions of general relativity. Real astrophysical environments include disks, magnetic fields, and messy plasma. The exterior spacetime close to the black hole can still be very well described by Kerr in many circumstances, but the surroundings add structure and emission that is not part of the vacuum solution. That is why we spend so much time on accretion disks. They are the lantern light in this case file, the glow that outlines the invisible. We can now step back and ask, how do black holes form? One route is the death of massive stars. A star fuses elements in its core, building heavier nuclei until fusion no longer yields energy efficiently. The core collapses. Depending on the mass and the details of the collapse, the remnant may become a neutron star or a black hole. There are thresholds and complications, including mass loss, rotation, and explosive dynamics. But the broad outline is solid. Between stellar mass and supermassive black holes, there may be an intermediate population, intermediate mass black holes, not as small as the remnants of single stars, not as large as the giants in galaxy centers. The evidence here is suggestive, but still developing. Some candidates appear in ultra-luminous X-ray sources, where the brightness exceeds what a normal stellar mass accretor would produce at the Eddington limit under simple assumptions. But geometry, beaming, and super-Eddington accretion complicate interpretation, so the debate remains careful and methodical. For the supermassive black holes in the early universe, there is an open puzzle. We see quasars when the universe was young, and yet their black holes are already enormous. How did they grow so fast? Several possibilities are under investigation. They might start as heavier seeds, formed by direct collapse of massive primordial gas clouds. They might grow through mergers of smaller black holes. They might experience periods of unusually rapid accretion that exceed the standard Eddington limited picture under certain models and conditions. It may be more than one mechanism working together. This is the tone I like most in science. Confidence where the evidence is strong, humility where the evidence is still accumulating, and a steady pace, because nature does not hurry to explain itself. Now, I'm going to reopen the folder and lay out the main pieces again, slowly, like arranging tools on a cloth: mass, spin, a horizon defined by causal structure, a disk defined by angular momentum transport, radiation shaped by gravity, motion, and plasma physics, and measurements that rely on patience, calibration, and repeated checks. From here, we slow our pace. The science remains the same, and we simply take it in with softer steps. We revisit each concept from a slightly different angle, the way a careful investigator circles back to confirm a detail in gentler light. The science remains the same, but we take it at a slower walking pace. We revisit each concept from a slightly different angle, the way a careful investigator circles back to confirm a detail in softer light. Let's return to the horizon, but keep our voice calm. A horizon is defined not by a material surface, but by the paths light can take. Outside, some light rays can escape to far distances. Inside, none can. This is not because light slows down locally to below its own speed. Locally, in a freely falling frame, physics remains normal in the sense of special relativity. The difference is global. The overall geometry does not provide an outward, future-directed route. It can be soothing to picture space-time as a kind of landscape, though we'll keep the metaphor light. Far away, the landscape is nearly flat. Near the black hole, the landscape becomes steep in a relativistic sense. And inside the horizon, the downhill direction corresponds to decreasing radius in a way you cannot reverse, just as you cannot reverse time on your own world line. Even that statement is not a claim about feelings or force. It is a claim about the structure of time-like trajectories in that geometry. Now, the phrase singularity appears in the folder, and it can feel sharp, so we will handle it gently. In the classical solutions, there is a region where curvature invariants can diverge. That is what is meant by a singularity in a technical sense, but we do not have a complete quantum description there, and many physicists expect that the classical picture is replaced by something else at extremely small scales. Importantly, none of the primary observational evidence for black holes requires us to know the detailed microphysics of the central singularity. Our evidence is built from the exterior. So, we shift our attention outward again to the region that glows. The accretion disk. A disk is a compromise between falling and orbiting. Gravity pulls inward. Angular momentum resists collapse. The result is a slow spiral. Not a plunge, a drift. A steady inward migration as angular momentum is transported outward. If the disk is thin and orderly, its inner edge often lies near the ISCO. That edge is not painted on by hand. It emerges from the dynamics of stable orbits in curved spacetime. Once gas moves inside the ISCO in the thin disk approximation, it can plunge quickly toward the horizon. The radiation efficiency of accretion depends in part on how deep the disk can extend before that plunge, which is why spin through the ISCO can influence luminosity and spectral shape. There is a serene way to hold this in your mind. Picture a series of rings, each ring representing a radius in the disk. Each ring has a temperature and therefore a characteristic glow. Outer rings are cooler, radiating at longer wavelengths. Inner rings are hotter, radiating at shorter wavelengths. When you sum them, you get the disk's overall spectrum, like a chord made of many soft notes. Above and around, there may be a corona, hotter, thinner, more variable. Soft photons rise from the disk and meet energetic electrons. They scatter, they gain energy, and then some return to the disk, where they are absorbed and re-emitted, or reflected with atomic fingerprints. Those fingerprints are then warped by relativity, by Doppler shifts from fast orbital motion, and by gravitational redshift. The result is a spectrum that carries a map of the inner region, a map written in light. To measure spin in practice often requires independent measurements of mass, distance, and inclination. The disk model has parameters, and nature rarely hands them all to us for free. So astronomers combine methods. They use dynamics for mass, parallax or other distance indicators, binary geometry for inclination. Then they interpret the disk spectrum or the reflection features to infer how close the inner edge can be and what that implies about spin. Now, we take a calm detour into the method itself, because methodology is soothing. A black hole is invisible, but science is not guessing. Science is constraint. Science is error bars. Science is repeated observation. You do not need to see a thing directly in ordinary light to know it exists. You only need consistent, converging evidence across independent channels. In the galactic center, the channel is orbital motion. Stars trace ellipses. Their speeds rise as they approach periapsis. Their paths reveal a massive central object. Another channel is millimeter interferometry, reconstructing a ring-like brightness distribution at horizon scales. Another channel is variability and flares, timing signals from hot plasma near the black hole. Each channel has its own systematics, its own weaknesses, and its own strengths. Together, they form a coherent story. The Event Horizon Telescope is a beautiful example of calm collaboration between physics and engineering. Telescopes scattered across Earth observe at the same time. Atomic clocks keep time with extraordinary precision. Data are recorded, shipped, correlated, calibrated. Then reconstruction methods build images that represent the most likely brightness distribution consistent with the measurements and the constraints. This is not a single snapshot from a camera. It is a carefully assembled picture from pieces of a Fourier plane, built with caution and cross-checks. The ring, the dip, the scale, the agreement with predictions based on mass and distance measured in other ways. These are the kinds of convergences that make a detective nod quietly and close the folder with a steady hand. Now we move to gravitational waves, and we take our time because the sequence is naturally paced. First, a slow orbit, then a faster orbit, then a chirp that rises in frequency and amplitude as the black holes draw closer. This part is called the in-spiral. It can be modelled with post-Newtonian expansions, when the black holes are still relatively far apart. Then comes the merger, where the fields are strong and fully nonlinear. Numerical relativity is used to solve Einstein's equations directly in this regime. Then comes ringdown, where the final black hole relaxes, and the signal can be approximated by a sum of damped oscillations. Those damped oscillations are like tones that fade. They are not perfectly steady notes. They decay as the black hole sheds deformation in gravitational radiation, and the frequencies and damping times depend on the remnant's mass and spin. So in principle, if you measure enough of these modes well, you can test whether the remnant is consistent with a Kerr black hole, as general relativity predicts. This is sometimes called black hole spectroscopy. Even if you never perform those tests yourself, it is calming to know what the data contain. A pattern, a fingerprint, a way that gravity sings. Not loudly, but cleanly when you listen with instruments sensitive enough to measure distortions smaller than an atomic nucleus across kilometers of baseline. Now let's drift back to the notion of only a few parameters, because it is one of the most restful ideas in this subject: mass, spin, and, mathematically, charge. In the astrophysical universe, charge is usually negligible because plasmas neutralize quickly on large scales. So the practical identity of an isolated, settled black hole is close to two numbers: mass and spin. The rest of the detail lives in the environment, in the disk, in the jet, in the companion star's wind, in the magnetic fields and turbulence that decide how matter glows. If you want a calm way to picture this without leaning on drama, you can think of the black hole as a boundary condition, a compact object with a particular space-time outside. Then you let gas flow in from a larger scale astrophysical context. You solve for what the gas does. You compute what it radiates. You compare to observations. You adjust within uncertainties. You check consistency across wavelengths. And slowly, the case file becomes thick with converging lines of evidence. Now we let ourselves rest in the slow spiral again, because spirals are naturally hypnotic, and this one stays scientific. A parcel of gas in the disk orbits many times before it drifts inward appreciably. Its angular momentum is transported outward through stresses, often linked to magnetized turbulence. As it drifts, it moves to a slightly lower gravitational potential energy. The energy difference appears as heat and radiation. So the disk is not just falling, it is converting orbital energy into light. Some accretion flows are not thin. At low feeding rates, the flow can become hot and radiatively inefficient. Energy can be carried inward with the flow rather than radiated efficiently at each radius. This is one reason Sagittarius A star can be relatively dim compared to the brightness you might naively expect for a black hole of its mass. The engine is there, but the fuel supply and the radiative efficiency determine how much light escapes. Now we open another pocket in the folder labelled Light Near the Hole. Photons near a black hole follow curved paths. Some escape directly. Some are bent around and escape later. Some are trapped, or nearly trapped, orbiting near the photon sphere for a short time before choosing a fate. This lensing creates rings and arcs and amplification patterns that can, in principle, be detected when we have enough resolution. The Event Horizon Telescope ring is one kind of manifestation of this physics, shaped also by the emitting plasma. This is a good place to slow down with a few short lines, like gentle footsteps in a hallway. Gravity bends light, motion shifts frequencies, curvature warps time, plasma glows where it heats, and we infer the invisible from the visible. Now, because this is a case file, we also record what we do not know yet. We do not have a complete, experimentally confirmed theory of quantum gravity. We do not yet fully understand the detailed origin of many timing features in accreting systems, like some quasi-periodic oscillations, even though their scaling with mass suggests a deep connection to gravity-driven timescales. We do not yet know the dominant pathway by which the earliest supermassive black holes assembled their mass so quickly. And that is fine. In science, open questions are not holes in the story. They are the edges where the story is still being written. Now we allow a quiet quantum coda, but we keep it gentle and proportional. Black holes, in semi-classical theory, have a temperature. This is the Hawking temperature, which scales inversely with mass. For astrophysical black holes, this temperature is extraordinarily tiny. So tiny that Hawking radiation is negligible compared to the cosmic microwave background and other astrophysical processes for black holes of stellar mass and above in most practical contexts. But conceptually, it teaches us something profound. Horizons behave like thermodynamic objects. They can be assigned an entropy proportional to their area. And that connection between geometry and information continues to inspire research. If that feels abstract, you can hold one clear fact. Entropy here is not a moral judgment. It is a count of possible microstates consistent with macroscopic parameters. And the area scaling suggests that the information content of a region may be tied to its boundary in surprising ways, an idea that echoes in the holographic principle. We won't push deeper than that, because the goal is rest, and the science is already beautiful at the surface. So we return to what we can measure with confidence: orbits, spectra, images, waves, and the slow, careful reconstruction of a hidden object's properties. Now we begin a longer drifting walk through the same territory, repeating the essentials in slightly different forms, the way a calm mind turns a stone in its hand. You do not need to follow every sentence. You can let the words pass like a slow stream. The content remains accurate, and the pace remains soft. Consider the simplest non-rotating black hole again. Outside, space-time is described by a metric that depends only on mass. The geometry tells clocks how to tick and rulers how to measure distance. A clock deeper in the gravitational well ticks differently relative to a distant clock in the sense that signals sent outward are redshifted. This is not because the local clock feels slow. Locally, it ticks normally. It is the comparison between different gravitational potentials that yields time dilation. The event horizon appears where a particular coordinate description can misbehave, but other coordinate systems pass through smoothly. This is a reminder that coordinates are tools. They are not the territory. A coordinate singularity can be removed by choosing a better map. A physical singularity cannot be removed by relabeling, and that distinction is one of the quiet strengths of general relativity as a geometric theory. Now consider a rotating black hole again. The Kerr spacetime depends on mass and spin. Spin introduces an axis. It breaks perfect spherical symmetry. It produces frame dragging, affecting how orbits precess and how stable circular trajectories behave. This is why spin measurements require intrinsically relativistic phenomena. Newtonian gravity does not encode spin effects in the same way. Now, accretion again, but slower. Accretion is a transport problem. Matter must shed angular momentum to move inward. So disks are not simply piles of gas. They are dynamical systems where magnetic fields and turbulence create stresses. Those stresses heat the gas and shape the radiation. The disk's emission encodes where the heat is deposited and how efficiently photons escape. Some systems cycle through states. A bright thermal dominant state where the thin disk is prominent. A harder state where the corona and comptonization are stronger. Transitions that reflect changes in accretion rate, geometry, and magnetic structure. These behaviors are not random drama. They are patterns arising from plasma physics in strong gravity, and they can be studied with time-domain astronomy. Now, the detective's favourite principle returns: independent checks. In the galactic centre, stellar orbits give a mass. Then millimetre imaging yields a shadow scale consistent with that mass and distance. Then near-infrared flares and astrometry probe motion close to the horizon. Each technique has its own systematic uncertainties, but the story aligns. In mergers, the inspiral waveform gives a chirp mass and other parameters. The merger and ringdown provide information about the remnant. And across a population of detections, we infer distributions of masses and spins, and we test whether the signals match general relativity's expectations. This is not a single dramatic proof. It is an accumulation of evidence. Now we let the mind settle on a particularly calming result. In many contexts, the details of complicated collapse are radiated away as gravitational waves, and the final black hole relaxes to a simple state. That relaxation is not instantaneous. It is a damped process, a ringdown, a fading oscillation. And in that fading, the universe tells us, quietly, what the final object is. Now, we take one more long loop through black hole growth, because it connects accretion to cosmic history. A black hole can grow by accreting gas. It can also grow by merging with other black holes. Accretion is often the dominant channel for building the largest masses, because electromagnetic radiation reveals active accretion in quasars and active galactic nuclei. But mergers contribute as well, especially in hierarchical galaxy formation, and in the early universe, the question of seed formation remains open and fascinating. Direct collapse models propose heavy seeds forming from massive gas clouds under conditions that suppress fragmentation into normal stars. Merger-driven models propose growth through repeated coalescences. Super Eddington phases propose that under certain disk structures and radiative transfer conditions, accretion can temporarily exceed the standard Eddington limited picture. The likely truth may involve a mixture, depending on environment, metallicity, and cosmic time. And here is a gentle grounding point. Even when big questions remain, the local physics of horizons, disks, and relativistic orbits is solid. The same equations govern a stellar mass black hole in an X-ray binary and a supermassive black hole in a quasar, scaled by mass and shaped by environment. Scale changes timescales, scale changes temperatures, scale changes the cadence of variability, but the underlying geometry is the same family. Now we slow further into a very gentle technical meditation, still accurate, still grounded. Physicists often use geometric units where the speed of light and Newton's constant are set to 1. In those units, mass can be expressed as a length scale. The Schwarzschild radius becomes proportional to that mass scale. This is not a trick. It is a reflection of how, in relativity, mass and energy shape spacetime, and spacetime has both temporal and spatial measures that can be related by fundamental constants. This unit choice makes some equations look clean and quiet. 2m appears where you might expect a radius. Light cones can be drawn without carrying many constants, but the physical meaning remains the same when you translate back. It is simply a convenient ledger for the math. Now, we linger on the EHT process one more time, because it is restful to focus on careful procedure. A wave arrives at one telescope. The same wave arrives at another telescope thousands of kilometers away, delayed by the geometry of Earth. By correlating the signals, we measure interference fringes. Those fringes sample the Fourier transform of the sky brightness. By collecting many baselines and many Earth rotation angles, we fill in more of that Fourier plane. Then we reconstruct an image consistent with the samples and with physical constraints. This is why the EHT is sometimes described as using Earth itself as part of the instrument. The rotation of our planet provides changing baselines, like slowly turning a key under a gentle light. And because the target, like Sagittarius A star, can vary during the observing window, reconstruction must also account for time variability. The final ring is therefore not a single instant, but a consistent structural signal extracted from careful analysis. Now we return to jets, but only softly. Jets are often associated with magnetically dominated regions near rotating black holes. In some pictures, the inner disk can enter a magnetically arrested state, where strong magnetic flux accumulates and influences accretion. In such environments, rotational energy extraction can be efficient, and jets can become prominent. But jets also depend on the broader environment, the available magnetic flux, and the details of the accretion flow. So the presence or absence of a jet is not a simple on-off trait of being a black hole. It is a property of the system. Now, one more quiet loop through gravitational waves. The inspiral signal encodes orbital energy loss. The phase evolution is measured with exquisite accuracy. Matched filtering compares data to predicted waveform families. The detection is not just hearing a chirp, it is statistical inference across a bank of models. Then parameter estimation yields posterior distributions for masses and spins. Then populations teach us about formation channels and astrophysical environments. Here is another set of short lines, like the soft closing of drawers: signal, model, inference, cross-check, and slowly, understanding. Now we let the quantum coda return, but only as a lullaby of scale. Hawking temperature goes down as mass goes up, so astrophysical black holes are effectively cold. Their evaporation times are far longer than the age of the universe for stellar mass and larger black holes. So the practical astrophysics is dominated by accretion and mergers, not evaporation. Yet the presence of temperature and entropy at all ties together gravity, quantum theory, and thermodynamics in a way that continues to guide theoretical work. Now the folder begins to feel complete, not finished forever because science keeps moving, but complete enough for rest. A horizon defined by causality, a disk defined by transport, a ring and a shadow defined by lensing and plasma emission, waves defined by inspiral, merger, and ring down, and a few parameters that summarize the core object, mass and spin. From here, the case file settles into gentle repetition, the way ocean waves settle into a steady rhythm. You can let each paragraph arrive and pass. Nothing needs to be held tightly. We are simply walking the same path again and again with soft steps. In classical general relativity, the defining feature of a black hole is the event horizon, a one-way boundary in spacetime. Outside, signals can reach infinity. Inside, they cannot. This is a global statement about causal structure, not a local material barrier. Coordinates can make the horizon look strange, but better coordinates cross it smoothly. Most astrophysical black holes spin. Spin introduces frame dragging and changes the locations of stable orbits. The innermost stable circular orbit often sets the inner edge of a thin disk. The disk's spectrum and reflection features carry information about the strong gravity region. By combining independent measurements of mass, distance, and inclination with disk models, astronomers can estimate spin in some systems. Accretion disks convert gravitational potential energy into heat and radiation. Magnetic fields and turbulence transport angular momentum. The corona can upscatter photons, and reflection can imprint broadened atomic features. Jets can be launched when magnetic structure and rotation align in the right way. And the brightness of a black hole system depends as much on its feeding environment as on the black hole itself. We detect black holes through orbits, spectra, images, and waves. Binary dynamics can reveal masses too large for neutron stars. Stellar orbits in the galactic center reveal a supermassive object. Millimeter interferometry reconstructs ring-like emission consistent with a shadow. Gravitational wave detectors measure chirps and ring downs consistent with black hole mergers and their final Kerr-like remnants. Black holes form from stellar collapse and grow through accretion and mergers. Intermediate mass black holes are plausible, with candidates under active study. Early supermassive black holes present an ongoing puzzle, with multiple growth pathways under investigation. Quantum theory suggests black holes have temperature and entropy, but for astrophysical masses, Hawking radiation is practically negligible. And still, the conceptual link between horizons and thermodynamics remains one of the deepest clues we have. Now, very softly, we close the folder, not because the universe is finished, but because you do not need to keep reading to rest. The desk lamp hums, the case file sits in its place, mass, spin, horizon, disk, ring, wave. A quiet physics of gravity, steady and exact. And as the words thin out, you can let the last idea remain, simple and calm. We learned black holes by studying what surrounds them. We measured the invisible with patient instruments and careful inference. And the universe, in return, offered a clean boundary and a handful of parameters, like a tidy signature at the end of a long, elegant proof.